Good morning, sir and madam. I am Anushmita Kumar of ECE from Technomen Sunday of batch 2026. I am presenting our final year project that is a self-balanced warehouse surveillance bot. This project is done under the guidance of Aditi Tokta. First, there is content page. This is the outline of our presentation. And first, I will introduce the introduction. In introduction, we have written that our project is a self-balancing warehouse surveillance bot. It is designed for continuous warehouse monitoring. It uses an ESP32 for balancing and Raspberry Pi for AI processing and a camera for live video streaming. We use yellow Persian pipe based on fire detection to identify hazards in real time, and all alerts are displayed on a MERN web dashboard for remote monitoring. Then the second part of introduction. Here we wrote that the robot balances itself using an IMU sensor and a PID controller, allowing it to move smoothly on two wheels. It can easily navigate narrow warehouse paths for security. Our system uses OTP-based authentication, and every detection is stored for future references. We've given some literature review, that is a review of the project. From our literature review, we found that the existing system mainly use static CCTV cameras which and traditional fire sensors, which have a limited coverage. Our solution combines AI-based detection, a self-balancing mobile robot, cloud storage, and a web dashboard, making warehouse surveillance smarter and efficient. Then the problem statement. Problem statement, the aim of the project is to develop an autonomous robot that can monitor warehouse, detect hazards like fire and obstacles, and send real-time alerts. It also provides the live video streaming and stores all the events for future monitoring, reducing the need for manual inspection. Then we have given the picture of the system architecture. This diagram shows the overall architecture of our system. The ESP32 controls balancing and movement, while the Raspberry Pi performs AI-based detection and video streaming. The live feed is securely sent through Cloudflare Tunnel to our MERN web application, and recordings are stored in AWS S3 remote access. Now I'll hand over this to my other member.
Hello, myself Soham Datta. I am a member of PC department and I am the SS8 gen, and we demonstrate our smart city surveillance automatic robotic system. It is the full architecture of our system, and the Raspberry Pi and ESP32 board all balancing and machine learning parts are included. Here we show the full architecture of our system. Bot system control system. There are three mainly control system. One is IMU sensor, which is PID modules and PID control and gesture control. Autonomous system and ultrasonic sensor or camera, and manual system. Manual system means manual system in manual you can control the bot. Hardware component. This is the hardware component we are using in our project. One microcontroller, ESP32 board, one microprocessor, Raspberry Pi 4B, one Pi camera, and one buck converter to convert the voltage high to low for our Pi. This is all other hardware system. There are many types of sensor, IMU sensor, ultrasonic sensors, and we are using GB37 motor driver for our project to controlling our bot. One motor driver they are using, one spice guide receiver we are using. This is our workflow of detection part of our Raspberry Pi 4B, and by which we are detecting our object, many types of object, and our fire in this project. There are many types of layer. One in video capturing layer. In video capturing layer, we use Pi camera module RAV 1.3. By this module, we capture video, live stream video, live video stream. One is processing layer, the quality size and converting the frame to 640 and 640 frame rate, 640 and 640 frame size, and 640 480 resolution. AI description for AI detect part. We use YOLOv5 for object detection, which is help of OpenCV and Coco. And in fire detection part, we are using pre-trained dataset from overflow overflow any automated by after detecting the object we bounding there are any bounding blocks and class level boundaries block select the object and show a green box for the object and red bounding box for any type of fire and return which is the object and who will fire which is the fire streaming any in this video, we are record the live stream in 5 minutes slot for our history in this part. For review this other system, for recording, we are use mp.mp4. In this recording system part, we are record the video from Raspberry Pi camera. Raspberry Pi camera record in 5 minutes short to Raspberry Pi SD card slot SD card. After the SD card, the video is uploaded to the AWS and AWS to our web page. To check the history videos of for any kind of need we are using this storage part for remote controlling and remote detecting. Now I hand over the other part to my friend and project group member Subhas.
Myself, Swasthchandra Unayan, TNSL batch tutorial. This slide is showing the video tunneling workflow. Basically, we are taking the input from the Pi camera module and host a local flash server. The server application processes the video feed and generate a live streaming endpoint for a real-time access. Basically, we are using here Cloudflare tunneling to uh, convert the public URL to a fixed permanent URL. Here we have used the Cloudflare tunneling. The tunneling establishes secure outbound connection between Raspberry Pi and the internet. It exposes the local flash video streaming through a public URL without requiring port forwarding or a static public IP address. Here we are making a website to monitoring our camera and what is happening in front of camera. That's why we are making a website. There is we have used the Monster application. Using Monster, we are making website. The Monster application stores the manage and Cloudflare stream URL to its backend service. The React content retrieves this URL and embeds the live video feed into the dashboard for URL. Live stream delivered to the users. User can access the live stream using the website. In the next slide, we are showing the workflow of the our website. This is the workflow of our website, how it's working and how can user access the website. First of all, user can create a account using their email or password or Google sign-up. Both options are there. User can easily register their existing email ID, password, or existing Google account. Thereafter, the backend will send a verification code to the existing login email ID. There are 6-digit OTP. After OTP verification, user can access the overall website. The user can log in using their registered email, credential, or Google account. The system validates the provide credential and sends an OTP for an additional layer. This is the next step of the after OTP verification. Uh, JWT token will be created for a session. This token are valid for 24 hours. After 24 hours, token will expire and user automatically log out from the website. After login, user can access camera management, external service integration, remote monitoring. Camera management means user can add multiple camera using camera ID, location, and Cloudflare URL, permanent URL. Next, we are showing our website UI. This is our website UI. After successfully login, user can access the dashboard, camera, recording. Recording section means this is the history of the recording. We can backup it in our website and user can easily access anytime, anywhere. And next is alerts. Alerts means how many alerts are getting. These alerts can be stored in the alert section. This is the our UI interface of the website. And also Pi will send Pi camera will send a API call to our website backend, and in our website a notification alert notification pop-up will be showing uh, below the website.
Now start the self-balance mechanism. In self-balance mechanism, we use IMU sensor and ultrasonic sensor mainly, and one ESP32, one motor driver, and two gear motor. Here we use flight type to control our bot manually. This is the mechanism. Here are some checkpoint and startup link. ICM sensor used to control the self-balance state. Had the slice receiver used successfully linked to transmitter to accept the movement of the command. Mode section layer. After the mode section communication link, robot read transmitter input and select one three operation. Standstill mode, manual mode, or automation mode. Each automation mode ultrasonic sensors are used to detect the obstacle and determine the safe direction of movement. The convention motion target. Based on the selection operation, the motion target is generated. This is the precision of maintaining position. It is used by ESP32 models. The inner balance feedback loop. The ICM 20948 continuously measures the robot tilt and motion data safely yesterday using PID-based control algorithm. The ESP32 calculates the corrective action and drives the motor through the motor driver. This is the mechanism we use to maintain the balance in two-wheel self-balance mechanism. Now this is our bot looking like this is the ultrasonic sensor. This is the pulse scan receiver and Raspberry Pi and IR PCB board for ESP32 and this front part is in back part. This is the battery by which we are powering this bot. This is the AI detection part. Here we detect the object, which is a mouse, and here we detect the fire. We can see here the object is bounded by screen, and the fire bomb is also red, and label is also here.
now start the conclusion part. By this project, we we work with the to Evercam, ICM32, PIT based module, YOLOv5, ONNX fire detection module, and many types of things. Here by this we can do a self-balanced robot, which is all round over the organization and detect the object as a fire and multiple light chains. For this project, we take references from this kind of reference. Thank you.